This is my lab report for lab 3 black hole. For the introduction, the main formula used is Newton's second law, which is the change in momentum is equal to F net times delta t, and this can be broken down into parallel and perpendicular components. So we have change in momentum is equal to F parallel plus F perpendicular times delta t. And then when we take the derivative, we have the change in momentum over the change in time is equal to the change in momentum per change in time for each of the parallel and perpendicular components. And additionally, since the only force acting on the star here is gravity, we have the net force is equal to the gravitational formula, which is the gravitational constant g times mass 1 times mass 2 divided by the distance between the masses squared. And since we know that F net is equal to the dp dt, we have dp dt is equal to gravity constant times m1 times m2 divided by r squared. And since we're solving for the mass of the black hole, we solve for m2, and then we yield this formula, which we'll use to calculate the mass of the black hole in the computational model. So for the glow script model, the initial conditions were that the mass of the star is 2 times 10 to the 30 kilograms, and the time interval between each data point is a day. So we have 60 seconds times 60 minutes times 24 hours. So then that's what we use for the time interval of 1 day. And then we calculate the initial and final momentum vectors in lines 164 and 165. And then we calculate the change in velocity and change in momentum in lines 168 and 169. We calculate dp dt by doing the change in momentum over the change in time, so delta p over delta t. And since we stated before F net is equal to dp dt, in line 175 we set them equal to each other. Then we calculate the parallel and perpendicular components of dp dt and F net. So we have p hat is equal to the normal vector of p final, and then we calculate the magnitude, and we find F net parallel is equal to dp dt parallel, and we have F net perp is equal to dp dt minus dp dt parallel, just by rearranging that equation. Then finally, we calculate the mass of the black hole using the formula stated earlier, where we solved for m2. And for the results, the mass of the black hole is about 7.14 times 10 to the 30 kilograms. For the second part of the lab, we were instructed to create a computational model that shows a spaceship approaching the black hole and coming close to the black hole but not entering orbit, while also not crashing into the black hole. So to do this, we need to find the net force on the planet and ship. So first, we find the net force on the planet. So the first step is finding the position difference between the black hole and the planet. We find the unit vector for that, which is r1 hat, and then we find the force of the black hole on the planet using the gravitational formula. And then we find the gravitational force of the ship onto the planet using the same method. And then we find F net on planet is the force of the black hole on the planet plus the force of the ship on the planet. Then the next step is to calculate the net force on the ship, and the two forces acting on the ship are due to the black hole and due to the planet. So we repeat the same steps, and since the force on the planet, the force of the ship on the planet was calculated previously, we know that the force on the planet on ship is just the negative value of that same force. And then we find F net on ship is equal to force of black hole on ship plus the force of the planet on the ship. Then we update the velocity and position using Newton's second law for the planet and for the ship, and we have the planet's velocity is equal to the planet's initial velocity plus force of net force on planet divided by the mass of the planet times delta t, and then for the position we have the planet's position plus the planet's velocity times delta t, and we repeat these same steps for the ship. So my results found that if the ship's x speed is negative 14.5 times 10 to the 6, and the ship's speed in the y direction is negative 0.5 times 10 to the 6, we will have the ship approach the black hole without crashing. So the first discussion question was to discuss the differences between the net force and its parallel and perpendicular components and how they're different than the rate of change of momentum and its parallel and perpendicular components. So these are two separate quantities. The net force is the change in momentum over the change in time, while the rate of change of momentum is how fast or how slow momentum is changing. So in other words, net force is delta p over delta t, and rate of change of momentum is delta p. Finally, for the last question, it asks, what initial velocity would your spaceship need in order to enter some kind of orbit around the black hole? So for the spaceship to enter an orbit, the spaceship must go close enough to the black hole to be under its influence of gravity, but not too close to the black hole where it would crash, and not too far away where it would not be, the gravitational pull wouldn't be strong enough to pull it into an orbit. And through trial and error, I found that this initial speed should be about 9.6 times 10 to the 6 meters per second in order for it to enter a orbit around the black hole.